Uh, Today we will be discussing problems from the tutorial sheet number 4, which is based on linear transformations. The way this tutorial will be conducted is similar to the last one. Firstly, I'll go over some the solutions to the tutorial problems, and after each question, I'll wait for some doubts, and then in the end, some important problems from the practice problems have also been put in, so we'll discuss that also. So let's begin with the first problem. So the first problem says that we have a linear transformation f which goes from R5 to R3 and is defined as follows. And we need to find the basis for the null space and the range of f using Gauss elimination method. So f is a linear transformation that takes in a vector belonging to R5 and transforms it into a vector in R3 as per this given formula. So what we do is that we begin by first finding the matrix that is associated with f. And we'll find that matrix, which is the one which is in respect to the standard basis of R5 and R3. The dimensions of this matrix will be 3 cross 5, and that can be seen because it takes an input of 5 dimension and transforms it into a vector of 3 dimension. Hence, the size of the matrix will be 3 cross 5. On observing the formula for f given, we can see that A turns out to be this matrix. We can verify it, like multiply x1, x2, x3, x4, x5, the vector composed by these 5 numbers, and then applying the transformation A to it, we get these numbers. So the first row, when multiplied by this x1 to x5 vector, it will give us 2 times x3 minus 2 times x4 plus x5. And similarly, we can do that for element number 2 and for element number 3. Now we need to transform A to bring it to its row echelon form so that we are able to calculate the number of elements in the null space and the dimensionality of the null space and the dimensionality of the range of function f, which is determined by A. So we have the matrix A and we start doing elementary row operations. The first row operation that we do is that we exchange row 1 and row 2. Uh, we are doing this because we want to have a pivot at this place. The first pivot should appear at this place. So the exchange of row 1 and row 2 simply gives this transformed matrix. On this matrix, we make this entry, the 2 entry in the first row, and in the second column we make it 1, and for doing that we divide the first row by 2. And now once we have divided the first row by 2, we will get a 1 here, and using that one we'll eliminate this 0 that is present in the third row, so that we are able to make this column, we are able to get this closer to the row echelon form. So doing these two operations, we get a matrix that looks something like this. Now we do the same thing with the third column. So in the third column, since the first row already has a pivot here, in the second row we want the pivot to be present at the second position. Like in the third column, the second position should be a pivot. So in order to try to achieve that, we'll first make this 2 a 1 by dividing row 2 by 2, and then using this one we'll eliminate this 7. So that is done by subtracting 7 times row 2 from row 3. So this will, once we do these operations, we realize that the entire third row has been converted to zeros, and we get these 2 pivots here. So basically this is the row echelon form of A, one of the row echelon forms of A. Now this matrix is being represented by G of A. The question asked us to find the basis for the range of f and the basis for the null space of f. So range of F is also known as the image of F, and in terms of A matrix that represents F, it basically means the column space of A. So like to get an intuitive idea of this, what does range mean? Range means all the values that F can take, like we give it vectors from R5 and it will give us vectors to in R3. So all those values in R3 that are attainable by applying F to any vector in R5, that is called the range. And applying F on a vector belonging to R5 is same as applying A to that same vector. So basically we want all those values that AX can give us, and that is nothing else but the column space of A. So now from this matrix G of A, as we have already seen, column 2 and column 3 have pivots. So we have two pivotal columns, and uh, uh, out of 5 we have two pivotal columns. So these columns, the second and the third column of A, like if we go back to the question, 0, 2, 1 and 2 minus 8, 3 from were the second and third column of A, and hence they form a basis for the range of R, because these are the only linearly independent columns which are present in A. All else can be formed as a linear combination of these two vectors. And now the null space of A. So what is the null space of A and that of F? F basically it is the set of all x vectors, like all vectors say x, such that f of x is 0, which is the same as saying that we want all the solutions for Ax equal to 0, and that is nothing else but the null space of A. So to find the null space of A, we have to solve this equation, this homogeneous equation given by Ax equal to 0. So just writing out the equation Ax equal to 0, the elements of x have been denoted by x1, x2, x3, x4 and x5 here. So this gives us this equation. Like if you, the third row of A, that will give us 0 equal to 0. So just skipping that, this row, the second row will give us x3 minus x4 plus x5 by 2 gives us 0, and the first row will give this equation, equation 2. So as we see that since we had 5 columns and 2 were pivotal columns, so the rank of A was 2, and by the rank nullity theorem we know that rank of A plus nullity of A should be equal to 5. So the nullity of A is 3 here, and the non-pivotal columns, that is column 1, column 4 and column 5, they the the variables that correspond to these columns in this homogeneous equations are a free column. So we are free variables. So we set special values, like some easy values, such that solving these equations become easy. We set values of x1, x4 and x5, which are the free variables, to find the basis for the null space of A. So the first thing we do is put x1 equal to 1 and x4 and x5 equal to 0, and then solve these two equations. So basically, if we put x4 and x5 0, we'll get x3 0 from equation 1, and we put x3, x4, x5 0, we get x2 equal to 0 from equation 2. So this is our first vector. The second vector similarly put x4 equal to 1 and x1 and x5 as 0. So when we do that in this equation, we get the value of x3 from equation 1, which is equal to 1, and then from equation 2 we get the value of x2, which is minus 3. And the third vector is similarly calculated by putting x5 as 1 and x1 and x4 as 0, and then when we solve equation 1 and equation 2, we get this vector 0, half, minus half, 0 and 1, the whole the transpose of this gives us a 5-dimensional vector. The nullity of A was 3, and now we have got 3 vectors that represent the null space, like they form the basis of null space of A. So any others, solution of the form of ax of the homogeneous equation ax equal to 0 can be represented as a linear combination of these equations. So they form the basis of the null space of A and hence of F. So this was the first question. Are there any doubts? Okay. If anyone has any doubts, they can ask. I don't see any doubts, so I'll move on to the next question. You guys can ask questions relating to the problems that are being discussed in the chat box, and I'll respond them correspondingly. So I'll be moving on to the second problem. The second problem is similar to the first one, and it asks us, instead of calculating the basis for the range and null space of the linear transformation given, we need to find the rank and nullity if it is possible, along with obviously the range and null space. So the first one is very much similar to the previous question. The only difference is like the exact values, like the dimensions of this domain and codomain are different, and of the actual transformation is also different. Similarly, as we had found A, the transformation matrix associated with the given linear transformation T, this time since T goes from R2 to R2, we'll get a 2 cross 2 matrix, and the matrix is given by this 2 by 2 matrix 1 1 1 0. It is very simple to verify. Multiply this by x1 x2, so you'll get x1 plus x2 as the first element and x1 as the second element. So we'll convert A into its row echelon form, and this can be done by two simple operations. First, we subtract from row 2 row 1. So what this will do is this will make this element A21 as 0, and hence we'll get this in the form that we want, column 1 in the form that we want. And then we'll get a minus 1 at A22 because we are subtracting row 1 from row 2. So we multiply minus 1 to row 2 to get a 1 here. That will be a pivot. So as you can see that both column 1 and column 2 form a pivot for this matrix. Hence there are no pivot free columns. Basically, by using the rank nullity theorem here again, there are two columns, so the rank is 2 pivot columns, so rank is 2 and nullity therefore is 0. So nullity of A and hence of T is equal to 0. And because the nullity is 0, the null space is only this 0 vector. Because for any other vector, we would have had at least one dimensions for the null space. But that is not the case, as nullity is 0 and nullity is basically the dimension of the null space. So the null space consists of only the 0 vector. And since both the columns of A are pivot columns, rank of A is 2. And the range is, the dimension of range is 2, basically that is the rank, and hence the range is R2. So this was a very simple problem. Like the first part of problem 2 was very simple. The second part was a good problem. It is, what it is saying is that instead of working on real, like some real space like R2, R3, R5 as we have done before, we have these spaces from this C1 of 0, 1 to C of 0, 1. And the function is defined, the transformation, the linear map T is defined as you can see on the screen. Like it takes in a function f and what it does is it transforms it to f dash x into e raised to power x. So let's first understand what is happening here. This notation C superscript 1, 0, 1 is the set of all functions that whose derivative exists on 0, 1 and the derivative that we get is continuous on 0, 1. C01, that is this right hand side block, is the set of all functions that are continuous over the interval 0, 1. So like C superscript 101 means that it should be derivable and its derivative should be continuous, whereas C01 means that that function should be continuous on the range that is specified next to C. Interval, basically interval that is specified next to C. So first we need to find the null space of T. So the null space of T means that we need to find the set of all such inputs such that T of that input will give us 0. So say that F represents any element in the null space. So generalizing over F, we want T of F to be equal to 0. And what is T of F? T of F is basically F dash X e power X. And we want this value to be 0 in order to be able to find the null space of T. And the condition given is that X should belong to 0, 1 because that is the range over which we are working right now. This implies having f dash x into e power x equal to 0 implies that f dash x should be 0. And this is because e power x is never 0 in the interval 0 to 1. It goes from 1 to e. So it is and it is a continuous monotonically increasing function. So we don't get e power x doesn't ever attain 0 in 0 to 1. So in order to have f dash x into e power x equal to 0, we must have f dash x equal to 0. F dash x equal to 0 means that f is a constant function such that if we have f of x equal to c, derivative of f of x, that is f dash x, will be 0. So the null space of T is the set of all such functions, that is all such constant functions. Similarly, now we go to finding the range of this transformation. So how is the range? How do we go about this? Let's take any continuous function g, the g belonging to C01, meaning that g is continuous over 0, 1. So if we take f of x as this, like the integration of g of x into e power minus x, what do we see? We see that f of x belongs to C superscript 1 of 0, 1. And why is that so? That is because see, g of x by definition is belonging to C0, 1. So g of x is continuous on 0 to 1 and e raised to power minus x is also continuous on 0 to minus 1. So gx into e power minus x is continuous, and if we are taking its integral, so f is also continuous, and since f is the antiderivative of a continuous function, it is itself differentiable. So f belongs to this C superscript 1, 0, 1. And if we take T of f of x, so now what was T? T was saying that for any input f, we do f dash x into e power minus x. So this will give us g of x, like because by virtue of the definition of how we defined fx. Means that for any g that belongs to this space, we are able to find at least, like we are able to find f such that T of f will give us this g. So range of T is therefore the entire space C01. Now one thing to notice is that this is like for each g of x we can get infinitely many f of x, because you can add, once you integrate, you can add any constant and then also it will satisfy this given thing. So it's not like a one-to-one mapping or anything of that sort. For each g of x, you can find many functions f such that T of f equal to g of x. But this g of x can be any function in C of 0, 1. So we are able to get all the functions in C of 0, 1. So hence the range of T is this only. Any doubts in this? Okay, I don't see any doubts in this. So I'll move on to the next question. So the next question, the problem number 3. So we want to find a linear transformation T from R3 to R3 such that the set of all vectors that satisfy this equation. We have three-dimensional vectors, denote them by x1, x2, x3, like it, first element is x1, second element is x2, and third element is x3. We want them to satisfy this equation. And all the vectors that satisfy this equation should be in the null space of T. So how do we go about this? First of all, notice one thing, that this equation 4x1 minus 3x2 plus x3, they form a two-dimensional subspace of R3. So we'll call that subspace C. So how do we say that it's a two-dimensional? We know that this is the equation of a plane, like 4x1 minus 3x2 plus x3. This will give us a plane in the three-dimensional space. And a plane is basically a two-dimensional subspace of R3. So all the vectors that satisfy this equation lie on the plane that we choose to call C. Like all that, those set of vectors we have chosen to call C. So it is a two-dimensional subspace of R3. So we only need two independent vectors in order to completely define this whole plane. That is, we need two independent vectors to find a basis of this subspace. So how do we go about it? First, we take up any random vector in this place. So how do we do that? V1 we take by putting x3 equal to 0. If we put x3 equal to 0, we get 4x1 minus 3x2 equal to 0. So like in order to get like neat looking integer functions, we just put x2 as 4 and x1 as 3 to get v1. And another vector that we get is by putting x1 equal to 0. So if we put x1 equal to 0, in order like one choice of x2 and x3 would be 1 comma 3 in order to have again integer numbers. So this v1 and v2, they completely define this plane. Like any other vector could be written as a linear combination of v1 and v2. Any vector in C could be written as a linear combination of v1 and v2. That is because, see, here we have a 0 and here we have a 0. That is because of which we are able to do this. So now we have v1 and v2 which form a basis of C. We extend this set of v1 and v2 by adding v3 to it such that v1, v2, v3 form a basis of R3. So how do we do that? We pick an R3 that is perpendicular to the plane of v1 and v2. So how do we pick a vector that is perpendicular? So recall that these coefficients will directly give us, like the coefficients of x1, x2, x3 in this plane will directly give us the a vector that is perpendicular to this plane in R3. So that is 4 minus 3 and 1. We can also do this by multiplying, like by taking the dot product of v1 and v3. So like as you can see, we'll get a 0 when we multiply the corresponding elements of v1 and v3 and add them, and similarly the dot product of v2 and v3 is also 0. So this indeed means that v3 is perpendicular to the plane of plane described by C. And v1, v2 and v3 together form a basis of R3. Now what does the question say? The question wants us that the null space of X should be described by C. So if we have any X that belongs to C, it should mean that T of X equal to 0. And if T of X equal to 0, it means that that X should belong to the C, the plane C. So we define the transformation function in this way. T of v1 we put as 0, T of v2 we put as 0, and T of v3 we put as a vector of 1s, that is 1, 1, 1 transpose. So this bold one means a three-dimensional vector composed of 1s. So how does this help us? one thing to notice is that if we define t for a basis of R3, then we have basically given the complete definition of t. And how is that? Because any vector in R3 could be written as a linear combination of v1, v2 and v3, because v1, v2, v3 form the basis of R3. So because we are able to write them as a linear, any vector in R3 as a linear combination of v1, v2, v3, and by using the fact that t is a linear transformation, we'll get like some constant multiplied by t of v1, some constant multiplied by t of v2 plus some constant multiplied by t of v3. So like t of that vector could be written in terms of t of these three vectors. So now let's go on proving why this definition of t is a good choice and it satisfies the condition that we want it to satisfy. So let's say we have any x that belongs to C. First we'll prove it in the forward direction. So since x belongs to C and v1 comma v2 together form a basis of C, x could be written as a1 v1 plus a2 v2, where a1 and a2 are some unique the a1 and a2 are some unique scalars and they uniquely define x with respect to this basis. So if we take t of x, what do we get? T of x is basically t of a1 v1 plus a2 v2, and because t is a linear transformation, we could separate a1 v1 and a2 v2 with respect to t and pull out a1. So this will give us a1 t of v1 plus a2 t of v2, and t of v1 and t of v2 by definition are 0. So we get 0. So what do we get? That if x belongs to C, then t of x is 0. Now we do it for any vector. Like we could do this like in the reverse direction also. Like if t of x equal to 0, then also you could try to prove it that x, it would mean that x indeed lies in this. So that is like I've just put in a simple form here. So if for any x belongs to R3, we have t of x equal to 0. So since x belongs to R3 and v1, v2 and v3 together form a basis of R3, x could be written as sum a1 v1 plus a2 v2 plus a3 v3 for some unique reals a1, a2, a3. And by, like we have that t of x equal to 0. So this would imply that t of this expression is 0, and we would separate this out as done before. So this first part would become 0 and we would get a3 t of v3 equal to 0, and t of v3 is just ones, like is a vector of ones. So we would get a3 equal to 0. So which is the same as saying that x belongs to the plane C. Because if we put a3 equal to 0, x would become a1 v1 plus a2 v2 for some real numbers a1 and a2, and this a v1 and v2 form the basis of C. So linear combination of v1 and v2 would also lie in C. So like if so we have proved it in the reverse direction also, that if t of x equal to 0, it would imply that x belongs to C. So like if we see for any general y, like just defining on how we will be able to calculate t of y for any general y belonging to R3, y is a1 v1 plus a2 v2 plus a3 v3, because again because v1 v2 v3 form a basis of R3, and using the linearity of t, we can write t of y as a1 t of v1 plus a2 t of v2 plus a3 t of v3, and this t of v1 and t of v2 will go to 0, and we'll just get a3 into the vector of 1s, which is the value of t of y. So we see that t is a valid linear transformation that satisfies the given